This will be a relatively short discussion. We'll take one more look at K-maps, and then we'll introduce a new topic of gate delay, or in more general terms, we're going to introduce time, which will be a critical aspect of sequential circuits, which is the topic of our next discussion. We described K-maps as a visual method to simplify logic. They're relatively easy to use when we only have 2 to 4 inputs. With more than 4 inputs, they become three-dimensional, and you might be better off using the Klein-McCluskey method. To use the K-map, we map minterms to individual cells. There's a relationship when we talk about those cells in that adjacent cells differ by a single bit. As an example, let's construct a 4-input K-map and consider minterm number 4. With inputs D, C defining the rows and B, A defining the columns. The minterms, you gotta be careful. This one here is 2, and this one is 3. Then it's 4, 5, 6, 7. I'll be real careful because number 8 ends up down here. With the K-map done, we can now look at minterm number 4. 4 is adjacent to 5. We'll show there's a 1-bit difference. 4 is adjacent to 0, a 1-bit difference, to 12 with a 1-bit difference, and if you go all the way around, number 6 is adjacent to number 4. 4 compared to 0 is 0, 1, 0, 0, 0, 0, 0, 0, where this is the single bit difference between them. 4 to 5, 0, 1, 0, 0, to 0, 1, 0, 1, where this is the single bit difference. 4 to 12, the difference is here. And finally, 4 to 6, with the difference in this position. The last thing to remember about K-maps is that we circle adjacent cells. Where the rules are, we can circle 2, 4, or 8 cells. And don't forget the corners. As an example, let's go back to this K-map and let's see if we can find F is equal to C0 A0 or CA or D0 CB. Before we start, take a good look at this equation. I think you'll agree that this is a sum of products equation. No question about that. It is not a sum of minterms. We know that because this is not a minterm, this is not a minterm, and not even this is a minterm. Also, this equation may or may not be optimized. With that said, let's put everything into the K-map and see what we can see. The first term is C0 A0. So here's C0, and A0 is here and here. So it looks like that first term describes the 4 corners. The next term, CA, would be defined by the C rows and the A columns, which means that describes the 4 minterms in the center. This last term is in the D0 C row and the B column, which equates to minterms 7 and 6. 7 was previously selected, so we can add a 1 here to minterm 6. Now that we've got all the numbers entered, we can take a look at the K-map and see if this is indeed optimized. We can circle these 4 in the middle. That one's easy. We'll grab the 4 corners. And it looks like we could grab minterm 6 either this way or this way. Given the choice, I'll select this way, which is described as D0 C, and then it looks like we're in the B column. The 4 corners are described as C0 and then A0, and these 4 in the middle are described as C and then A. So our optimized Boolean equation is C0, A0, or CA, or D0, C, B, which means our original equation here was indeed optimized. By the way, there are times when we don't care which value the output takes. We call that a don't care. Here's an example. Suppose you're dealing with a decoder chip. We'll let that chip have 4 inputs, so D, C, B, and A, which present a hex word, and that decoder chip is then used to drive a 7-segment display. For this particular example, let's assume that input 0000 equates to the numeral 1, all the way down to input 1001, which will equate to the numeral 9. And for our purposes, we will not define anything higher. So A to F are don't cares. The reason we don't care is that we're making an assumption that this input will only provide an output with digits 0 through 9. For this example, let's focus in on this segment, which is known as the E segment. Our compact sum of minterms for that particular segment goes something like this. Segment E is required for a 0. So we'll write minterm 0 here. It is not required for a 1. It is required for a 2. It's required for a 6. And finally, it is required for the numeral 8. With that said, let's make our K-map with inputs DC and BA. Here's minterm 0. Here's 2, 6, and finally 8 is way over here. So those are the minterms we're sensitive to. But remember, we don't care about A through F. So what we're going to do is we're going to put X's on those particular terms. Here's minterm 10 and 11, 12, which is 8 plus 4, 13, 14, and finally 15. Now, the beauty about don't care operators is we can make them zeros or ones, whichever makes our logic easier to build. For this example, it would be nice if both of these don't cares would become ones. That way we can use the entire B A0 column. With minterm 10 as a 1, we can select the 4 corners, which is another very easy piece of logic. And I believe we're done. The circuit simplifies to, let's see, C0 and A0 to describe the 4 corners, and everything on the right here is defined by the B A naught column. So the E segment is C naught A naught or B A naught, with the understanding that these min terms became zeros and these two became ones to simplify our logic. Let's see. Let's take one last look at combinational logic, which includes the K-map. It includes the truth table. It includes various Boolean equations, including the sum of products and the sum of min terms. We also have gate level representations, including different styles such as the bubble and my personal favorite, the array. In the future, we might take a look at those hardware description languages, including Verilog and VHDL. The main point in all of this is to remember that we can go from different forms. For example, we can go from the K-map to a truth table, the K-map to a Boolean expression, the K-map to a gate, or from a gate to Boolean, or from a gate to a truth table. And in the future, we'd like to move to Verilog and VHDL, which will greatly simplify things. You could say that everything we've done with combinational logic has been about conversions between various forms. Let's look at one more example. Suppose there is a function dCBA described as C or dB A naught or D naught C naught B naught A. Let's go ahead and enter that directly into K-map and then see if we can come up with the sum of min terms. To save a little time, I'll write in the min terms this time. The first term is C. Looking at the K-map, we see that C exists only in these two rows. We can therefore put a 1 for min terms 4 through 7 and C through F. This implicant, D, so there's the D row, and then B A naught would put it in that column. So that's these two right here, min terms E and A. This min term, D naught C naught, would be in this row, B naught A. We interpret that as a 1. As for simplification, we already knew this one, so that's C. Looks like this can be combined, so that is D naught and B naught A. It looks like these two can be combined, which gives us D B A naught. So our optimized expression is C plus D B A naught or D naught B naught A. It looks like this term was simplified. Let's move on and talk about time. As an example, consider input B and input A, and let them change as a function of time. Let A have twice the frequency of B. As for outputs, let's see what things look like with an AND gate and an exclusive OR. The AND gate is written as B and A, that output will be low for this period of time, and then it will go high for one cycle here. It will be low again and high for one cycle here again. You can see how that lines up. Here's something you might have noticed. If A is the least significant bit and B is the most significant bit, together they make a number. This is a 0 where both A and B are low, a 1 where B is low, A is high, a 2 where B is high, A is low, and a 3. And then that pattern repeats, 0, 1, 2, 3. You can see that the AND gate, B and A, is high only for the number 3, which is exactly what you saw in the truth tables. So let this be B ANDed with A. So B ANDed with A will only be high when BA input is 3. While we're here, let's make the exclusive OR truth table. And that will be high when A and B are different. So 0, 1, 1, 0. We can go ahead and translate that up here into our timing diagram. So A and B are the same. They're different here. They're different. They're the same. Different, different, same. I strongly suggest you spend some time with this timing diagram. You will see it on the exams and quizzes. It will also be very important that you be able to work through time when we arrive at our sequential circuits. Speaking of time, let's talk about gate delay. Consider this circuit. There's an inverter as well as an AND gate. Input B and A. Therefore, this F, so our F is equal to B naught A. One of the things we need to consider is this critical path right here. How long does it take an input on B to be seen as an output on F? To answer that question, let's make a few assumptions. We will assume a wire has a delay of half of a nanosecond. A NOT gate has a delay of 0.75 nanoseconds. The AND gate has a delay of 1 nanosecond. And finally, when we get to them, we'll let the OR gate have a 1 nanosecond delay. Starting here at input B, we encounter a wire. So there's our first half nanosecond. This inverter, 0.75 nanoseconds. A wire leading to the AND gate, yet another half nanosecond. The AND gate itself, 1 nanosecond. And finally, another wire. The total delay is therefore 0.5 plus 0.75 plus 0.5 plus 1 plus 0.5 nanoseconds, which I believe is equal to 3.25 nanoseconds. Remember, that is a description of the critical path. It describes how long it takes for an input, which is seen here on B, to propagate to the output here on F. Here's another example, slightly more complicated. Let this be a 3-input system using an array style. Sensitive to min-terms 3 and 4. The critical path includes one of these inverters, so we may as well start here. There's a wire, the inverter, a wire, a AND gate, a wire, an OR gate, and finally another wire. So the total delay is 0.5 plus 0.75 plus 0.5, which gets us here. Now we go through the AND gate, to the OR gate, through the OR gate, and finally to F. I believe that works out to 4.75 nanoseconds, which may not seem like much, but I would argue that that's a very significant delay. Here's why. Remember that frequency is equal to 1 over period. In this case, our period is 4.75 times 10 to the negative 9, which gives us a frequency of about 210 megahertz, which is extraordinarily slow when you consider that a modern CPU has a core that can run at 5 gigahertz. Anywho, that finishes up our discussion for today. I have one more thing I'd like to talk to you about. Everything we've done up to this point has dealt with combinational logic. We built it with a variety of gates, which together were described as a cloud of circuitry. There were inputs and there were outputs. And it was very clear that the outputs were 100% dependent on the inputs. But now we shift to sequential circuits by including memory. That memory typically takes one of the outputs from the combinational circuitry and routes it back to the input. That changes everything because the outputs are now dependent on the inputs and the contents of the memory.